All right, hello everyone, and welcome to our 7th lesson of Unit 4, which is on types of reactions, specifically acid-base, redox, and precipitation. So today's understanding is that a substance can change into another substance through different processes, and the change itself can be classified by the sort of process that produces it. Today we're looking into acid-base reactions, which involve a transfer of one or more protons between different chemical species. Redox reactions, which involve transfer of one or more electrons between chemical species. And precipitation reactions, which frequently involve mixing ions in aqueous solution to produce an insoluble ionic compound. And just to remember our AP Chemistry solubility rule that all sodium, potassium, ammonium, and nitrate salts are soluble in water. If it does not have one of those 4 ions present in the salt, then you can assume it is insoluble. And then finally, we are going to go over oxidation numbers. Oxidation numbers may be assigned to each of the atoms in the reactants and products in a redox reaction, and this is just an effective tool to identify whether the species are being oxidized or reduced. An acid-base reaction involves the transfer of a proton or H+ ion from one species to another. Remember that we use the word proton and H+ ion interchangeably as they mean the same thing. And that's because if you have a hydrogen atom, it is 1 proton and 1 electron surrounding it. So if we were to get rid of that electron, we are left with only a proton. And remember from our previous video, the acid is going to donate the proton and the base is going to accept it. A common example is when a strong acid like hydrochloric acid reacts with a strong base like sodium hydroxide. The H+ from the acid is going to combine with the OH- from the base. That's going to form water, and then our leftover ions, in this case Na+ and Cl-, will react to form NaCl. So overall, acid-base reactions typically form a salt and water. So we know in an acid-base reaction, a proton is transferred from one species to another. When an acid donates a proton, it becomes a conjugate base. And when a base accepts a proton, it becomes a conjugate acid. So by identifying the acid and its conjugate base and the base and its conjugate acid, we can see exactly where the proton moved. And if we can match each species with the conjugate partner, that's going to confirm that we do in fact have an acid-base reaction. So with these 2 example tables that we're going to do here, they're not always going to look exactly like they're formed in this case because we most of the time will have a base that forms an ionic compound. So your base is going to be the anion most likely, and then your base will be paired with a cation to form an ionic compound. So it's not going to look exactly like this in the tables, but it does at the particle level. And we'll do an example of that after we do these tables. So remember, an acid donates a proton, which is H+. So if we have HF, that is going to become F-. HNO3 will become NO3-. H2CO3, we're only getting rid of 1 proton, becomes HCO3-. And then moving on to our bases, remember our bases accept a proton, so the conjugate acid would just be adding an H+. And now let's do an example with one of our acids from this table. Let's pick HNO3, and one of our bases from this table. Let's pick ClO-. So we have our acid, HNO3. Normally the application for the base would be it is paired with an cation to form a neutral ionic compound. So let's use sodium. So Na plus and ClO minus would form NaClO. And so this would be an acid-base reaction because the hydrogen moves to bond with the ClO minus base. And that's going to form our conjugate acid, HClO. And then left over, we have our nitrate ion, NO3 minus, and our sodium ion, Na plus, and that's going to form an ionic compound, NaNO3. So this is an example of an acid-base reaction using that information with our acid and conjugate base and conjugate acid. So next up, let's talk about oxidation-reduction reactions, or what you will hear me call redox reactions. These reactions involve the transfer of electrons between chemical species. In these reactions, one species loses electrons, that's what we call oxidation, and the other species is going to gain electrons, which is called reduction. We can identify redox reactions by looking for a change in oxidation numbers from reactants to products. And one common example of a redox reaction that you can point out pretty quickly is going to be combustion reactions, because the substance reacts with oxygen, and since oxygen is in its elemental form, it's going to have an oxidation state of 0, and the electrons are going to be transferred in the process when it becomes a chemical molecule or compound. All right, in order to fully understand and to balance redox reactions, we have to be able to identify oxidation numbers. First, let's go over some general rules for identifying oxidation numbers. First is if you have free elements, which just means you have either one or multiple of the same element, that means the oxidation number for those atoms are 0. If you have a monatomic ion, let's say one of your reactants are Fe2+, that means your monatomic ion, its oxidation number is the same as its charge. So with Fe2+, the oxidation number would be +2. In neutral compounds, like an ionic compound like NaCl, just remember that all of the oxidation numbers have to add up to 0 because it's a neutral ionic compound. And then with polyatomic ions, just remember that the oxidation numbers have to equal the charge of the ion in total. So if you look over here at CrO4 2-, the oxidation states have to add up to 2- because that is the overall charge. Now let's go over some specific element rules for oxidation numbers. The first is whenever you have a group 1 metal in a compound, it's going to have an oxidation number of +1. Whenever you have a group 2 metal in a compound, it's always going to have an oxidation number of +2. Fluorine is always going to have an oxidation number of -1 when it's in a compound. Oxygen is usually -2, but there are 2 exceptions. If it's in a peroxide like H2O2, then oxygen is going to have a -1. If it's bonded to fluorine, since fluorine is more electronegative, then oxygen is going to assume a +2 charge. So just keep those 2 exceptions in mind. And then hydrogen can either be a +1 or a -1 oxidation number. It depends on what is more electronegative. Typically, with AP chemistry, we are bonding hydrogen with a nonmetal, so it's going to have a +1 oxidation number, but if it is bonded to a metal, then it's going to have a -1 oxidation number. So now that we know those rules, let's go ahead and do 2 practice problems. First, we have KMNO4. Now you can do this 2 ways. You can do it as an entire neutral compound because it's neutral and we know it adds up to 0. We can do it that way, or since we already know K is a group 1 metal and it has a +1, we can just focus on MnO4, which we know is a -1 for the polyatomic ion. Either way works. I'm going to do it both for you just so you can see what I mean. So let's start off with what I know. So I know K is a group 1 metal, which means it's going to have a +1 oxidation number. And I also know O, since it's not in a peroxide and it's not bonded to fluorine, it's going to have a -2 oxidation state. So because we know K is +1 and oxygen is -2 times 4 or -8, if this is balancing out to an overall charge of 0, which it is because it's in a neutral ionic compound, that means Mn has to be +7, because then we have a total of +8 and -8, which balances out to 0. The other way to do this is using the polyatomic ion, because we're clearly trying to find the oxidation state of manganese because we already know potassium and oxygen. So since MnO4 is a polyatomic ion that is equal to -1, you can technically find it this way as well. So we know -2 times 4 is equal to -8. And we know the overall charge has to equal -1. So if I add that with X being manganese and I bring that to the other side, that means X has to be equal to +7. So you can do it either way. They both work and they both make sense logically with chemistry. Whichever way works better in your head, do it that way, as long as you get the right answer. Now, binary ionic compounds like this one should be a lot easier because we are so used to doing this already with forming the formula or the name of ionic compounds. So we know oxygen is -2 times 3 is going to give us an overall -6 on this side, which means this side has to be +6. And since we have 2 of them, each iron would have an oxidation state of +3. So iron would be +3. Oxygen would be -2. And I just want to verify that you understand that you are not writing +6 and -6 here. You're doing the individual oxidation number for each atom. So each iron atom and each oxygen atom. So in a redox reaction, whatever is losing electrons is being oxidized and whatever is gaining electrons is being reduced. And you might hear me call whatever is being oxidized the reducing agent and whatever is being reduced the oxidizing agent. That's honestly just slipping my mind when I'm talking about redox reactions. That is not actually assessed on the AP exam, but I wanted to give you that information just in case I said it and you had no idea what I was talking about. So most important thing, whatever is being reduced is gaining electrons and whatever is being oxidized is losing electrons. A common way to remember this for a redox reaction is using the phrase oil rig. Oil stands for oxidation is loss of electrons and rig stands for reduction is gain of electrons. All right, so let's identify what's being oxidized and what's being reduced. Remember from our rules, if an element is by itself, that means it's going to have an oxidation number of 0. And zinc and sulfur as the reactants are by themselves, which means their oxidation numbers are 0. Then in the compound, we know zinc has an oxidation state or a charge of +2, and sulfur is -2, just because that's a ionic compound. That's a nice and easy way to identify those. Now, looking at this, we can see that zinc goes from a 0 or neutral charge to a +2. Now, we know from metal cations that when we go to a +2 charge, that means we lost electrons. So zinc lost 2 electrons, and you can write that as zinc formed Zn2 plus 2 electrons. So the electrons will be a product because we lost those electrons. And then sulfur gained 2 electrons because it now has an oxidation state of -2, which means the electrons are going to be on the reactant side. So we have sulfur, we're going to add 2 electrons, and that's going to give us sulfur with a 2- charge. So these here are what we call half reactions, and those are very important when we start balancing redox equations. But just for now, you need to know that when something is losing electrons, that is going to be oxidation, and your electrons are going to be on the product side. And when you are gaining electrons, that means it's being reduced and it's on the reactant side. All right, so now let's do a little bit more complicated one just because we have more atoms to solve for their oxidation numbers. First, we have MnO4 minus. Again, we did this one already. We already know oxygen has an oxidation state of -2. Because there are 4 of them, that means our total oxidation state for the oxygens are -8, and the overall compound has a charge of -1. So if we are solving for manganese, that means we're essentially solving for X, and when we solve for X, that's going to give us +7. So Mn has a +7 oxidation number. Then moving on to sulfite. Sulfite has a -2 charge, so when we add up all of the oxidation numbers, it needs to add up to -2. We know oxygen is -2 times 3 is going to give us overall -6. We want to equal to -2. So we are solving for S or X. And when we solve for X, that's going to give us a +4 oxidation number. Now moving over to the product side, we have manganese with a 2+ charge. This is a monatomic ion, which means the oxidation state is the same as its charge. So this is +2 for the oxidation state. And now we have sulfate. So sulfate is just one more oxygen. It's still equal to -2, but now we have a total of 4, which is going to give us -8. So when I'm solving for X or sulfur, that's going to give me +6. So sulfur on the product side is going to be +6, and oxygen is going to be, again, -2. So now from here, we need to identify what element is being oxidized and what is being reduced. Now remember, whatever is being oxidized is losing electrons. And when something is losing electrons, that means its charge is going to be getting more positive. So we're increasing our positive charges or positive oxidation numbers. And then whatever is being reduced is gaining electrons. And when we are gaining electrons, because they are negatively charged, we are increasing our number of negatives. So we are increasing the negative charge or negative oxidation state. So I can see on all oxygens, I have a -2, which means oxygen is not being oxidized or reduced because its oxidation state in all components of the chemical reaction are -2. So now I'm looking at manganese and I'm looking at sulfur. I can see that in manganese, I'm going from a +7 to a +2, which means I gained negatives because I gained 5 negatives or 5 electrons. And because I'm gaining electrons, that means manganese is being reduced. Now let's look at sulfur. Sulfur goes from a +4 to a +6. Remember, when we're getting more positive, we are losing electrons. So that means sulfur lost 2 electrons, which means it was oxidized. So now that we are able to identify equations in which there is a loss or a gain of electrons, we know how to identify redox reactions. In our last lesson of this unit, we will go over how to actually balance them, but for right now, this is all you need to know. So our final type of reaction for today, which is a review, is precipitation reactions. These occur when you have 2 aqueous ionic solutions mixed and the ions rearranged to form an insoluble solid called a precipitate. In this example, silver ions from AgNO3 and chloride ions from KCl come together to form AgCl, which is insoluble in water, so it forms a solid. The remaining ions, K plus and NO3 minus, which are your spectator ions, stay dissolved in the solution. And so the key idea here with precipitation reactions is that it forms a product that does not dissolve in water, and that solid is called the precipitate. And then I just wanted to remind you again of the only solubility rule that you need to memorize for AP chemistry, which is that all sodium, potassium, ammonium, and nitrate salts are soluble in water. So if it has one of these 4 ions in the ionic salt, that means it will dissolve in water. If it does not have one of these 4, you can assume it does not dissolve in water or it is insoluble. All right, so let's do a net ionic equation example. What is the net ionic equation for a reaction that occurs when sodium chloride is mixed with silver nitrate? So we have sodium chloride. Sodium is a positive one. Chlorine is a negative one charge. So that's going to balance out to 0. So we only need 1 sodium and 1 chlorine. That does have sodium in it, so that's going to dissolve in water or be aqueous. Then we have silver nitrate. Remember, silver is always a positive 1 charge. Nitrate is a negative 1 charge. So again, they both cancel out. So we only need one of each, AgNO3. And because it has nitrate, it's going to be able to dissolve in water. And now we're going to make our new products. So sodium, the only other thing it can bond to is nitrate. So we're going to form sodium nitrate. Because it has sodium and nitrate in it, we know it can dissolve in water, so that's going to be aqueous. And then we have silver with a positive 1 charge bonding to chlorine with a negative 1 charge. And those do not have one of our 4 ions that dissolve in water, so we can assume that this is our solid. I also told you in previous lessons that AgCl is the most commonly assessed precipitate in AP chemistry, so just keep in mind whenever you see AgCl, it's your solid. So now let's go ahead and make sure this is balanced. Everything was a 1-to-1, so it is already balanced. And now let's do our net ionic equation. So in order to get the net ionic equation, you can do it 2 ways. You can do the long way by writing out your complete ionic equation and then canceling out your spectator ions, or you can just identify your solid and your reactants are going to be the 2 ions that make up that solid, which is what I'm going to do. So I know Ag is in AgCl, so I have Ag+. That's going to be aqueous on the reactant side. That's going to react with Cl-, which is aqueous on the reactant side, and that forms my solid product of AgCl. So that is your answer. Just because you are probably watching this video to learn, I'm going to show you the other way too. So first, to get the net ionic equation, you take your aqueous salts and break them apart into their constituent ions. So we have Na plus aqueous, we have Cl minus aqueous, we have Ag plus aqueous, and we have NO3 minus aqueous. Then we look at our products. Again, this is an aqueous salt, which means it's dissolved in water, so we break it apart into its constituent ions. Hold on, it's a mistake. And then AgCl does not come apart because it is not soluble in water, so it stays together. And then we identify our spectator ions and cancel them out. So spectator ions are ions that are present on both sides of the reaction. So that's going to be NO3 minus and Na plus. And then we are left with our net ionic equation, which we already did previously, which is Ag plus aqueous plus Cl minus aqueous reacts to form AgCl solid. So both ways work. The first way is obviously a lot faster, but the second way is technically how you do it. So whichever way you prefer. And before we wrap up this lesson, I did want to do one of the more complicated stoichiometry questions with our precipitation reaction. So this question says 20 milliliters of 0.1 molar sodium chloride react with 30 milliliters of 0.04 molar PbC2H3O22. What is the mass of the solid formed, and what are the concentrations of ions at the end of the reaction? So let's go ahead and start with our very first question, which is what is the mass of solid formed? So this is just going to be a stoichiometry problem where we take our reactants and convert them into our product. Now, this question did not tell us if one of them were excess or one of them are limiting, which means we need to solve for both of them to find whichever produces the smaller amount of solid. So before we start any of that, we need to have our balanced chemical equation. So we know our two reactants are NaCl, which is aqueous, and PbC2H3O22, which is also aqueous. And those are going to form our products. First, let's do our PbCl2, which it does not have any of the 4 ions in it, so I'm going to assume that's solid. And then we have our NaC2H3O2, which has sodium in it, so that is aqueous. So now let's balance our chemical equations. Our sodiums are balanced, our chlorines are not, so we're going to put a 2 there, which means we need to put a 2 here, and now we are balanced. So now that we have a balanced chemical equation, we can go ahead and solve for moles of NaCl and moles of our other reactant. And we can do that by using our molarity equation. We know molarity or concentration is equal to moles over liters. So if we want to get moles, we're just going to take our concentration and multiply it by liters. So first with sodium chloride, we have we have 0.1 molar, so 0.1 times 20 milliliters, which is 0.02 liters. So that means we have 0.002 moles of NaCl. And then for our other reactant, we have 0.04 for our molarity, and then we have 0.03 for liters. So that's going to give us 0.0012 moles of PbC2H3O22. So now that we have moles of our two reactants, we can go ahead and solve them into mass of our precipitate so that we can get the actual mass of solid that can be formed. So first step, since we're already in moles, is to just do the mole ratio. So for NaCl, I have 2 moles of NaCl in my balanced chemical equation, and I have 1 mole of PbCl2. And then because it's asking for mass, I like to just convert both of them to mass since I have to get the molar mass anyways. And now let's get the molar mass of PbCl2. So we have 2 chlorines, so 35.45 times 2, plus our 1 Pb or lead, which is 207.2. That gives us a molar mass of 278.1 grams. So now I'm going to solve for both of these. So using the NaCl first, 0.002 divided by 2 times 278.1 is going to give me 0.2781 grams of PbCl2. And now let's do the same thing for our bottom equation. So 0.0012 times 278.1 is going to give us 0.33372 grams of PbCl2. So remember, whatever is smaller is going to be our theoretical yield. So this is the actual answer to this first question, what is the mass of the solid formed? Which means we know that NaCl is going to be our limiting reactant, and PbC2H3O22 is going to be our excess reactant. But the answer to the first question was what I circled there, and then looking at sig figs, we have 3 sig figs, 3 sig figs, 3 sig figs, and 3 sig figs. So our answer needs to be 3 sig figs, so we're going to erase that one. So our final answer for that first question is 0.278 grams of PbCl2. Now the next part of this question is what I would consider the harder part, which is really conceptually trying to understand what it's asking. So it says, what are the concentrations of ions at the end of the reaction? So we just found out that 0.278 grams of PbCl2 is formed. We also found out that NaCl is our limiting reactant and our other reactant is our excess reactant. Now what that means is that since NaCl is our limiting reactant, all of the Cl- ions were used to create PbCl2, which means in our final reaction beaker, there will be no Cl- ions present in the water. It will all be used to form the solid. Now for lead, that is not the case because the lead acetate here is our excess reactant, which means we still had leftover lead in the reaction beaker after lead chloride was made. So that means when all of my precipitate is formed, I'm going to have 3 ions in my reaction beaker. I'm going to have Na plus, I'm going to have acetate or C2H3O2 minus. Those are our 2 spectator ions. And I'm also going to have leftover Pb2 plus ions because those are my excess ions after our PbCl2 was made. So let's start off with the easier of the 3, which are spectator ions. Let's go ahead and solve for those. And because they don't actually change and they're just floating around in the water the entire time, we can just take them from our original moles of our reactants. So first we have 0.002 moles of NaCl. If I want to get my Na plus, I can just say that in 1 mole of NaCl, I have 1 mole of Na plus ions. So that means I'm going to have 0.002 moles of Na plus ions in the reaction beaker, so that's one of them. Then for our other one, our acetate ions, again, I can use my reactant that I already have the moles of. In 1 mole of PbC2H3O22, I have 2 moles of acetate ions. So that means I'm going to have 0.0024 moles of acetate. And then for the trickier part, let's go ahead and try to find the concentration of Pb2 plus ions that are left over. So in order to do that, I'm going to take my actual amount of precipitate that I was able to make, which is 0.278 grams of PbCl2, and I'm going to convert that back into our reactant PbC2H3O2, and then get my actual number of Pb2 plus ions that were used, and then subtract that from our original. So first step is to get that back into moles. So we're going to divide by the molar mass. And then we know that was a 1-to-1 ratio. So now we're back in moles of lead acetate. So we can do 0.278 divided by 278.1. That's going to give us 0.001 essentially moles of PbC2H3O2 used. So we can subtract that from our original here, which gives us 0.0002 moles of PbC2H3O2 left over. And since we know that's what's left over, we can convert that into just Pb2 plus ions to get how much remain of that. So since it's only 1 Pb in that equation, we know we are left with 0.0002 moles of Pb2 plus in our reaction beaker at the end. So now we have our moles of our 3 ions that are present in the reaction beaker at the end of the reaction. Now we need to get the concentration of those, and we know concentration is moles over liters. So we're going to take that and divide it by the total liters, which is 20 plus 30 milliliters. That's going to give us 50 milliliters, or 0.05 liters. So we take these three numbers and divide them by 0.05. And these numbers up here would be your answers for this question. All right, so now I would like you to look at these 6 reactions and tell me whether they are precipitation reactions, acid-base reactions, or redox reactions. So go ahead and pause this video and see if you can name them all. All right, so the first one, my biggest clue is that I have elemental zinc on the left and then zinc in an ionic compound on the right. And then same with hydrogen, I have it by itself on the right, but in a molecule on the left, which tells me I'm going to have a change in oxidation state. So this is going to be a redox reaction. And just a brief summary of that, remember, zinc by itself is 0, hydrogen by itself is 0. With HCl, we know hydrogen's paired with a nonmetal, so hydrogen's going to have a positive 1, chlorine's going to have a negative 1. We know zinc has one oxidation state of positive 2, which means each chlorine is negative 1. So we can see our zinc is going from a 0 to a positive 2, which means it lost, so zinc is being oxidized. And hydrogen is going from a positive 1 to a 0, which means it gained an electron, so that is being reduced. All right, then for our second reaction, calcium hydroxide reacts with hydrochloric acid. The H plus ions from the acid combine with the OH minus ions from the base to form water. So that means this is going to be an acid-base reaction. In the third reaction, silver nitrate and hydrochloric acid react to form solid silver chloride. That should give you an idea that this is a precipitation reaction because we have two soluble ionic compounds reacting to form a solid, so that's going to be a precipitation reaction. The fourth reaction also shows an acid reacting with a base to form water and a soluble ionic salt, so that's going to be another acid base. And then for our fifth example, again, we have two soluble ionic compounds reacting to form a solid or precipitate, and then a soluble ionic salt. So this is going to be another precipitation reaction. And then the last one, I can see I'm forming a liquid and a solid. So because it's not aqueous product, I know that's not precipitation. And then it's not an acid base. So I'm going to assume this is redox. So let's go ahead and check our oxidation states to make sure. So sulfur is a -2, lead is a +2. Remember, in H2O2, oxygen has a -1, and hydrogen will have a +1. In water, oxygen has a -2, hydrogen has a +1. And then sulfate, we know, equals -2, which means lead has to be +2. And in sulfate, oxygen is -2, and then sulfur is going to be +6. So then we can see that our lead is not being oxidized or reduced. Our sulfur, on the other hand, is. It's going from a -2 to a +6, which means it lost 8 electrons. So sulfur is being oxidized, and then our oxygen is being reduced because it went from a -1 to a -2. So this is a redox reaction. All right, I hope that makes sense. If you have any questions, please let me know. And next lesson will be on acid-base reactions. I hope you have a great day.